Hi, we need to prove these two algebraic fractions, the difference between them is equal to this algebraic fraction. But here's the clue. When you look at the denominator of this right hand side, you can see it's the product of this denominator and this denominator, which gives us a head start to know that they brought together these two algebraic fractions, and that's what we'll do. We'll subtract one from the other, which means we can just cross multiply in this direction and this direction and then simplify. So we'll take the left hand side and work with it and then show that we arrive at what we have on the right hand side. Let's get cracking. So we have n minus 2 brackets 3n minus 1, and that's minus n into 3n add 1. Our denominator remains the same, but we'll bring them together to multiply to get n into n minus 2. We'll leave that as it is. Now we'll clear the brackets and see what we have. 3n squared minus n minus 6n add 2. And we have a minus here. A minus n times 3n will give us minus 3n squared, and then we have minus n. We'll leave our denominator as it is. Now this cancels with this, because this is minus 3n squared and this is add 3n squared. And all we need to do is group and simplify like terms. What we have is minus n minus 6n, which is minus 7n, and this gives me minus 8n, and we have a positive 2 here. So our numerator now is 2 add, not 2 minus, I'm sorry, 2 minus 8n. Our denominator remains the same, n into n minus 2. And this proves that what we have on the left hand side is actually equal to what we have on the right hand side, because we've gone through algebraic manipulation and arrived at what we have on the right hand side. And that's how you prove this algebraic equation. Thanks for watching this video. Hi, we're given these these four numbers, and they're Hi, here we have four numbers represented by expressions, and we're told that the sum of the first two expressions is 36. So the sum of this and this one is equal to 36. So we can write that as 2x add 2, add that to 3x minus 1 is equal to 36. And then we need to work out the value of the median of the four numbers. We know the median is the middle number. We'll come to that later. Let's find out what x is equal to if we know that the sum of these two is equal to 36. That gives us, we have a 2x and a 3x, which is 5x. We have 2 minus 1, which is 1. That's equal to 36. So we know that 5x is equal to 35. So x must be equal to 7. So now we can go ahead and find out what these numbers are. And it'll make it a lot easier for us to work out the value of the median. So the first number, 2x add 2 will be 7 2's 14, add 2, which is 16. Then next here is 7 3's are 21 minus 1 gives us 20. Here is 7 4's 28 minus 6 gives us 22. And lastly, 7 5's are 35, take away 2 will give us 33. So these are 4 numbers that were represented here as expressions. We've solved this equation for x, and x is equal to 7. It's the same x occurring in each one of these. Just to check, is 7 2's are 14, add 2 is 16, 7 3 is 21, take away 1 is 20, 7 4's are 28, take away 6 is 22, and 7 5's are 35, take away 2 will give us 33. So we know for sure those are 4 numbers. Now the median is always the middle number, but we have an even number here of items or data. So the median, when it's even number of items, is the sum of the middle 2 and divide by 2, which is the average of it. So we add 20, add 22, and divide that by 2. And that leaves us with 42 divided by 2 is equal to 21. So 21 is our median of this list of data. First, we found what x is, and that helped us to calculate the number that each of these expressions represented. In order to find a median when it's an even number of items, we must add the middle 2 numbers and divide by 2, or you can say we found the average of the 2 middle items. Thanks for watching this video. My name is Alistair. Any questions or comments are welcome. Please like, follow, or subscribe for more videos like this. Bye for now. Hi, this is Harris Maths. Prove the sum of any 4 consecutive integers is not divisible by 4. First, we'll let n represent the first integer. So first integer is n, and then the other 3 integers will be n add 1, n add 2, and n add 3. So these are our 4 integers. Now we need to find the sum of these. So their sum is n add 1, add n add 2, add n add 3, and this totals 4n add 6. Now to find whether it's divisible by 4, we need to divide by 4. So dividing by 4, we have 4n 6 divided by 4, so 4n over 4 at 6 over 4. Now this gives us n add 3 over 2. Now since n is an integer, n add 3 over 2 is not an integer. Thus, the sum is not divisible by 4. By 4. And that's the proof showing that the sum of any 4 consecutive integers is not divisible by 4. Thanks for watching this video. My name is Alistair. Any questions or comments are welcome. Don't forget to follow, like, and or subscribe for more videos like this. Bye for now. Hello. Prove that the sum of 3 consecutive integers is divisible by 3. Well, let's use n add 1 to indicate one of these integers. Now if n is 1, then this will be 2. We could also use, for the next, n add 2. So in this case, if n is equal to 1, this will be equal to 3, and so on. So we'll have 2, 3, and n add 3. So these are 3 consecutive numbers. These represent all consecutive numbers. If we substitute n in any one of these expressions, we'll get an integer, and there will be consecutive integers. So we'll add all of these, and this will give us 3n, add 6, and to show that it's divisible by 3, we factorize this expression. 3 into n, add 2. And this shows that the sum of 3 consecutive integers is divisible by 3. Next, we have proved that n add 6 all squared minus n add 2 all squared is always a multiple of 8. Well, we'll just try to expand this and see what we have. Expand n add 6 will give us n squared. Add 2 times the product of n and 6, that's 12n. Add the square of this, which is 36, minus, and we'll square n here, give us n squared. 2 times the product of n and 2, which is 4n. Add the square of 2, which is 4. Clear the brackets, n squared add 12n, add 36 minus n squared minus 4n minus 4. Now the n squared cancels with a minus n squared, that goes to 0. We have 12n minus 4n will give us 8n. And then we have 36 minus 4 will give us 32. And to show that this is always a multiple of 8, we factorize by 8. And this shows that n add 6 all squared minus n add 2 all squared is always a multiple of 8. Right, we're asked to prove the sum of two consecutive odd numbers is even. In proof, we always use 2n add 1 to indicate an odd number. So for instance, if n is equal to 0, then this would be the first odd number, 1. And if we use the next odd number to be 2n add 3, here this will be equivalent to 3 if n is equal to 0. So these are two consecutive odd numbers, or they represent that, and we'll sum these, and this is what we have. We have 2n add 2n, which is 4n, add 4, 3 add 1 is 4. To show that this is even, we factorize by 2 to give us 2n add 2. This indicates that this expression will always be even because it's multiplied by 2. And this finally proves the sum of two consecutive odd numbers is even. Here we have to prove that the sum of three consecutive even numbers is always a multiple of 6. Well, we start with the first even number, it's 2n. The next will be 2n add 2. You can try this, you can check this, substituting any value for n, any positive value for n in any one of these expressions. And the third will be 2n add 4. So these are three consecutive even numbers. We need to show that the sum of these is always a multiple of 6. So we have 2n add 2n add 2 add 2n add 4. This is equal to 6n add 6. And if we factorize, we can see that the sum of three consecutive even numbers is always a multiple of 6. Alright, what if we have to prove this equation? Well, we'll start with the left-hand side and see if we can prove that it's equivalent to the right-hand side. We'll clear the brackets. We have n squared add 2n add 1 add n squared add 6n add 9 minus n squared minus 10n minus 25. So this is our left-hand side. We've expanded. Now we'll simplify this, bring together all the n squares. We have this now is equal to n, look, we have how many n squares? 1, 2, take away 1, which will give us just n squared. We have 2n, 6n, which is 8n, minus 10n will give us minus 2n. gives us minus 2n. 1 add 9 is 10. Take away 25 will give us minus 15. So this is our quadratic expression, and when we look at the right hand side it looks like a quadratic expression that has been simplified or factorized. So let's factorize this. We have a is 1, c is negative 15, so our product is 1 times negative 15, which is negative 15. Two numbers when multiplied will give us this is minus 5 and positive 3. When added will give us negative 2. So we'll factorize this by writing n squared minus 5n add 3n minus 15, which is equal to, we factorize again, n into n minus 5 add 3 into n minus 5, which is equal to n add 3 is common to n minus 5. So this shows that we've proven what's on the left hand side here is equivalent to what's on the right hand side. That's all for now. If you like these videos and you'd like to see more, like, share and subscribe. My name is Alistair. Hi. Prove that cot theta add tan theta is identical to sec theta cosec theta. We'll start with the left hand side and we'll simplify it. So first we have cot theta, we'll write that as the reciprocal of tan theta. We're adding this to tan theta. Again, we'll simplify this because we have a reciprocal and the reciprocal of the reciprocal. So we can write this as 1 add tan squared theta over tan theta. At this point, we use the identity that 1 add tan squared theta is equal to sec squared theta. So we have a numerator now as sec squared theta over tan theta. So the identity that we use is 1 add tan squared theta sec squared theta. So now we can simplify this further by writing sec theta, sec squared theta as a reciprocal, so we can write as cosine theta times 1 over cosine theta. So we know sec theta is the reciprocal, or the sec theta is equal to the reciprocal of cosine theta. So sec theta squared is the reciprocal of 1 over cosine theta times 1 over cosine theta. Or we could have gone and written here as 1 over cosine squared theta. And we're multiplying this by 1 over tan theta. can also write that this is 1 over cosine theta times 1 over cosine theta times tan theta is sine theta over cosine theta. The reciprocal of that is cosine theta over sine theta, or cot theta. Now we can cancel here and here, so we're left with 1 over cosine theta, which is sec theta, and 1 over sine theta here, which is cosec theta. So in this proof, we proved that the left-hand side, cot theta and tan theta, is identical to the right-hand side here by ending up with sec theta, cosec theta, using the identity 1 add tan squared theta is identical to sec squared theta. Thanks for watching. I'm Alistair. Bye for now. Hi. We need to prove this identity, but because we haven't a proof as yet, we have to isolate one of the sides. And it's only fitting for us to do that with the left-hand side. We're in the brackets. We can clear the brackets, simplify, and see a way to express the left-hand side as equivalent to the right-hand side. So clearing the brackets, we have 1 add sec A minus cosine A minus cosine A sec A. Now because we have a minus 1 here, I'm going to simplify sec A here and leave sec A here as it is. If I simplify sec A here, I wouldn't be able to actually simplify this because I'll just have 1 over cosine A. So the aim here is to eliminate this constant 1. Minus cosine A is minus cosine A, and sec A is a reciprocal of cosine A. So this cancels out to minus 1, all of this, and that cancels out that 1. And so we're left with sec A minus cosine A. Now the next thing we want to do is to write this now as a reciprocal cosine A minus cosine A. The reason for that is that we're always in maths, we're always trying to simplify things, and to prove something is really included in it, is to simplify steps as you go along to prove something. So sec A we write as in reciprocal of cosine A. And again we can simplify this as 1 minus cosine A, cosine squared A over cosine A. Now we know that sine squared A and cosine squared A is equal to 1. That's an identity that we'll use here. So we can write this now as sine squared A over cosine A. Remember we used sine squared A at cosine squared A is equal to, or is equivalent to, 1. That's the identity that we used. here. Further to this, sine squared A is the same as writing sine A times sine A. So instead of writing using brackets, we just write sine squared A. Just a shortened way of doing it without using brackets. So we can write this as sine A times sine A over cosine A. And you should be able to see that we can write this as sine A tan A. So now we've arrived at the right hand side. The left hand side, we started with the left hand side here, clearing the brackets, we have arrived at the right hand side. So this is a valid proof of this identity. Thanks for watching. I'm Alistair.